Hello, everybody. It's the first Monday in the month. Welcome back to the Berlin Machine Learning Group meetup. As has become tradition, our September meetup is hosted by SAP. Prior to the pandemic, we met over at the SAP office on the Rosenthalerstraße, right in the center of Berlin. Presently, of course, we meet only virtually, but many thanks to SAP for having us tonight. Tonight's speaker is Moin Nabi. He will talk about continual lifelong learning. So we as human beings are not alone in that sense. The machines do have to learn too during their lifetime. Moin is a principal scientist at SAP AI Research here in Berlin, where he leads the SAP fundamental research efforts in machine learning. His role is mainly to design and develop simple and efficient machine learning algorithms that are broadly applicable across a range of domains, including computer vision and natural language processing. Moin has a scientific background. He published over 40 peer-reviewed conference and journal papers in the AI domain. He also co-invented over 20 patents related to the application of AI in industry. Moin completed his PhD in computer science at the Italian Institute of Technology in 2015. Since then, he has conducted research at the University of Trento as well as at the University of Washington. And as I said, Moin is presently at SAP. I'm very happy to have you here, and on behalf of the rest of the organizers, Abhishek, who is in the background, Trent and Daniel, please welcome Moin for tonight's talk. The floor is yours, Moin. Thanks.
Thank you. Hello, everyone. Thanks for the introduction and having me here. I'm pretty excited to be here today among you machine learning, AI, data science folks at Meetup Berlin, giving the talk on one of my favorite line of research, continual learning. So during this talk, I will explain some of the works that we're doing in our group at SAP AI Research on how to learn a model continually and adaptively in a lifelong manner. So the majority of the content in the slides is based on some of my recent works on this topic, which are published at AI venues, CVPR, CCV, ICCV. So the papers, codes, models, and lots of other methods are publicly available to access. So these papers are joint works done in collaboration with my SAP colleague, Tassilo Klein, SAP students, and our academic partners, and particularly this guy, Alexei and Enrico, my students, doing PhD on continual learning. Alexei was my student, and Enrico is still doing his PhD in continual learning, who are the first authors and the main contributors of these papers. So my job as a machine learning practitioner is playing with the data every day, and I'm particularly interested in helping the world processing huge amount of data of a variety of applications, from processing huge amount of enterprise data, which SAP is interested in, analyzing user experience in an organizational setting, understanding social media content, and so on and so forth. So sometimes people ask me, what is the magnitude of the data that you're talking about in data science? So these are some numbers. So this data is extremely gigantic. So processing it is indeed very difficult. And it was actually kind of impossible until a few years ago, even to imagine having machineries that can extract pattern out of this tremendous amount of data. But in the last couple of years or a decade, and after emergence of techniques, new machine learning paradigms, particularly deep learning and its family, the performance got improved sharply in many tasks, from computer vision, natural language processing, robotics, automation, and so on and so forth. However, looking at growth pattern of this data, we also see huge acceleration in data creation and curation. So to me, this data seems like a gigantic snowball rolling down the hill, growing massively and widely. So these are some statistics, mainly demonstrating the fast-paced creation of data only in social media these days. If you see from the pure data science perspective, I see no problem with that as long as we have machineries that can extract and use this data. However, if you look at to this data growth pattern from an algorithmic point of view, it's crucial to think about developing new machine learning algorithms which can exploit this enormous data adaptively and keep with extraction of understanding, the underlying concepts behind this this content in a sort of efficient and organic manner. So interestingly, we also observe a growth on the size of AI models. If you can think of these recent gigantic models such as GPT-3, CLEAP, and so on as the examples of that. So here you see in the left the data volume or data size. So x-axis is time and y-axis is the size of data shown in zettabyte. So for those of you who don't know what exactly is zettabyte, like maybe for Googling it, it's 10 to the power of 21 byte, a trillion gigabytes. So it's pretty, and it's like very huge. In the right, you see the number of parameters used in some recent deep models. So x-axis again here is time, but this time is the time of releasing of the model, and y-axis is the number of parameter in billion. So you see both are growing as expected, but what is probably more interesting thing to see here is that the growth pattern of the model size is even sharper than the data itself. So the data acceleration is kind of magnified in the model size. This is mainly because the common practice in the community is to simply accumulating the data over time, store them, and every time use this big combined set of data to retrain the model. And since the data is growing and getting bigger, also the size of the models need to be larger and larger to extract the pattern out of this gigantic data sets. So we are kind of happy with these models because we see the accuracy and the benchmarks are improving, but in the same time, it's also a bad news because these models are too gigantic to fit into or normal or daily machines, very costly or energy inefficient to be even used for inference, and probably impossible to train by any of us, except we have access to like huge pool of beefy GPU machines or something like that. But to me, there is even a worse news here, and that is the fact that with the exponential growth pattern we observe in the data, if we want to scale up the number of the parameters of the model in the same fashion that we're doing now, we will soon face AI intractability. Yeah, we will face soon, intractability in terms of memory and computation. So basically, the current models that you're using today are not scalable enough to be used for the future. Simply because this static way that we learn our current models implies storing everything in the world, from Big Bang moment till the end time, if you want. And this is a very shallow strategy in deep learning era that we need to think about it again and again. But we as human can do that. So the question is how human can handle this, or what are the mechanisms that our brain works based on? Human learning is extremely complex, and we are very far away from understanding the inner working of the brain. And just know that the human learning is continual and happens during the course of life. But at a higher level, the brain seems to use mechanism known as complementary learning system theory, or CLS in short. So what does CLS mean? So based on this theory, human and other mammals learns by storing compressed representation of temporally correlated experience in their hippocampus. So priority is given to salient or novel objects, and the hippocampus representation can be accessed soon after storage, enabling them to be used for inference and potentially using a mechanism called waking replay. So during sleeping, these representations are consolidated into neocortex, as you see here. So basically, a connection over these two parts of the brain for short-term memorization and long-term learning. All right, I hope I could convince you after this argument and introduction that the static way of learning that we're using mainly today is not scalable, and we need to explore more sort of continual learning paradigms similar to human, given the lifelong nature of the data. Otherwise, we would end up having a sort of AI intractability in the long run. Now let's define continual learning a bit more formally. In a typical non-incremental setup, usually data of all classes is available simultaneously. So, and we would pass it all at once to the model, of course, in a batch setting, compute the loss with respect to the output, and find the parameters of the model by optimizing whatever objective. right? So basically the straightforward training pipeline, as you probably know, and a lot of you are doing your everyday job. However, in the incremental continual learning setup, we have a time dimension as well, and the classes of interest appear to the model sequentially and continually over time. So basically, we see concepts are coming. It can be one class at a time or multiple, and the model has to be learned incrementally and over the course of data, curation. And so there are two general scenarios you can think of here. The first one is the case that the tasks are coming one by one during the training. So here, for example, the first task is distinguishing fish versus bird. The second one is airplane versus car, and etc. So the scenario is called task incremental learning, and the model is learned in a multi-head fashion. So we have separate heads for each task, and during the inference, we are given with a task identifier or task ID, which is basically says which task we need to do evaluation based on. And the classification will be done only on that task, right? The second scenario in continual learning is class incremental learning, which is a more generic and more difficult scenario of continual learning. In this setup, classes are coming one by one. The model is learned in a single head fashion, so to just have one head and only neurons of each new coming class will be added to that head. So there is no information about task ID here, and the inference need to be done with respect to the all classes seen so far. So in this setup, of course, it's more challenging, probably because the complexity of the task is growing over time, and this is a more preferable setup over task incremental learning. So there is no need here to have the task ID, but of course, in some application or particular use cases, maybe the task incremental learning setup is already sufficient, so no need to have the extra complication of the task incremental learning. Okay, so the continual learning problem looks very easy to solve at first, but it's actually very challenging to extend solutions from static learning to an incremental learning. To better show the difficulty of continual learning, let me walk you through a continual learning example and explain better what challenges we're going to face in a typical continual learning scenario. When seeing the first class, D0, in this case, let's say a class containing yellowfish, our model would be able to perfectly recognize yellowfish and distinguish it from whatever else. So the accuracy of the task 1 would be very high, say 1, but since it's the only type of fish it has been seen so far, it would think all fish are generally yellow because it's all the word for our newborn model. But word is more than yellowfish, and we have redfish and other type of fish as well, and the model need to learn all of them. So the problem of our current deep network is that after seeing a class of redfish, D1 in this case, the model would basically override its past knowledge and assumes that all fish are red and not yellow. This is a very known problem in deep networks called catastrophic forgetting. So given a fish classification task, the classification accuracy on the first class would drop significantly from 1 to 0.7 in this case, while the classification accuracy on the most recent class, redfish, would be very high. So this phenomena has been first reported in late 80s, and this classic paper you see here with this term, where this term has also been coined there. So the main reason behind this is the IID assumption in a stochastic gradient descent. So in a non-stationary learning setups such as continual learning, because we don't have the chances of having representative samples for all the classes in all time, the model would be updated and the weights will be overwritten only by the samples of the most recent class. And this happens very often, especially in deep networks with a huge number of parameters. So these accuracy curves is going to be, we're going to have this type of, this accuracy curves that you see in practice, but these accuracy curves are what we would like to have. We would rather to have a good classification accuracy on both classes. So we want to avoid forgetting in this case and recognize both red and yellow fish in the same time, say an accuracy over 0.9 for both classes. Yeah. In the same fashion, when seeing the next class, let's say an aquarium in this case, D3, not only we want to classify all the classes seen so far and the new class aquarium with high accuracy, as you see in the curve behavior, but also we want to be able to profit from the knowledge learned previously. In this example, the model should build upon the knowledge about fish and recognize it in a new context as a feature of a new class aquarium. So leading to a kind of faster learning of a new concept. So I show here. What I show here is the learning curve, which is happening in a quicker manner. So this is a desirable property we would like to have in continual learning setup. This is called forward knowledge transfer, which basically means the model should be able to rapidly adapt to see fish in a new situation, and this should lead to a more quick learning curve, as I show here. Everything sounds good, a high accuracy for all classes, and even a faster convergence for classes with relevant information or similarity. But in continual learning, we also want more than this. We also want to profit from the newly obtained knowledge in the previously seen context. So here, the model can improve the classification performance on different type of fish when seeing them in new context aquarium. This is called backward knowledge transfer. So the accuracy of the previously classes of redfish can jump from 0.93 to 0.99 after seeing fish in the class of aquarium. And finally, as we continue learning new classes from the data stream, which potentially can be never ending, we would like to ensure that our model is able to acquire knowledge about all the potential new classes that we possibly will see in the future. And so we want our model to scale with the growing amount of data. So basically the scalability problem that I have started with, which to me is a sort of a core problem in continual learning. So we want our model to scale in an efficient kind of sublinear fashion with respect to the data growth. Otherwise, there is no point or benefit in terms of parameter efficiency compared to retraining a new larger model from scratch. All right, these are the key challenges of continual learning, at least to my understanding, which I briefly explained. Catastrophic forgetting, basically overwriting the old knowledge about the world when learning new concepts, knowledge transfer in forward and backward fashion, providing us with faster learning curve or higher performance, model scalability, the growth pattern of data, with size and with the size of data, the growth pattern of the model size with respect to the data volume. And now let's see how these challenges are addressed in the literature. In incremental learning in general, and in class incremental learning in particular, the simplest way for avoid forgetting is to store some of the previously seen data and replay it when learning new concepts. There are a lot of methods based on this simple concept, starting from famous Carl till the more recent ones. These methods are called replay-based or rehearsal-based method, which are still kind of the most efficient and effective way, at least in the class incremental learning. So the replay-based continual learning literature is pretty rich. So there are a lot of methods proposed different ways for shrinking the memory size, making it more data efficient in a sense by selecting a subset of the samples instead of keeping all of them, keeping only the most representative samples or the most discriminative ones, and so on and so forth. That's why there are a lot of versions of replay-based continual learning method exist in the literature. However, in the core, the episodic memory or buffer has some fundamental issues. Apart from the memory constraint or scarcity of the resources that they might have in a lot of real-world applications such as mobile or IoT devices, there is data privacy or data ownership, which limits us to store samples and reuse them whenever we want. And think of data in medical domain or particular customer data that you cannot really have access to it all the time. There's also scalability, which I talked about a lot before. Storing samples is not really efficient and scalable. And last but not least, the fact that it's not biologically feasible. Basically, we as humans don't store and accumulate raw data in our brain to memorize them. To address this problem, we proposed dynamic generative memory at CBPR 2 years ago, which assumes that there is no access to real samples seen previously in the training, and instead train a generative model to memorize previous data. So instead of storing raw samples, we use a generative model, which is often way more data efficient and also privacy preserving. So we trained this generative model, G, continually, which in this case was conditional GAN or auxiliary GAN. So we embed an additional adversarial loss to the discriminator. So after training G, we propose to replay generated samples of the previous classes and instead of the real ones, which are not available anymore, to avoid forgetting in the task solver. So in this case, we have real sample of class T and stack them with the synthesized samples from the previous classes and replay for training the model. However, when training G in a continual manner, the problem of forgetting or overriding the parameters is now moved to the generator. What you see here is the output of the generator trained on the digits 6, 7, 8 from MNIST dataset. And it shows how fast the generator forgets to generate the digits. So the same problem happens even more severely for more natural images. So inspired by the neuroplasticity in the human brain, we propose to learn a sort of task-specific parameter mask for mitigating forgetting in the generator. So this mask, you see them in different colors, yes, can be learned in the same time with the adversarial training of the generator. So the binary mask here specify which network parameters or weights should be reserved and for a specific task, meaning that they can be reused but not changed during the subsequent learning. And this ensures forward knowledge transfer while mitigating the forgetting. So we reserve and reuse network parameters over time to alleviate overwriting on them, but it violates the model scalability, and we address that by expanding the generator network after learning every new task to make sure that the number of free parameters remains constant. All right, and so now let's zoom in and have a closer look on how these masks are actually trained. What you see here is the forward pass and the back propagation for the task in hand. So for each layer, we learn a task-specific mask from a real valid embedding matrix. And then we pass it through a sigmoid function for the sake of binarization, because these masks are binary, and finally obtain the effective weight matrix for the task in hand by simply computing the element-wise multiplication of the actual weight matrix W with the binary mask. So basically zeroing out what should not matter. During backward pass, we compute the gradient for the task T+1 as usual, but then multiply it with the reverse of the binary mask we computed before. With that, we are zeroing out the gradient for the previously reserved parameters, and we can make sure that the reserve parameter for the task T will not be touched, so no more overwriting on any form. Now let's look at the result. So we evaluated two variants of our method, basically masking weights and masking neurons on different benchmarks, and outperform both episodic and generative memory-based method as you see here. But what probably more interesting is to see is the behavior of our generator. What you see here is the synthesized samples by our method for different classes and data set. When I saw the samples for the first time, it reminded me of what we see in our dreams. So pretty much like kind of blurry hallucination, but at the same time contain the key visual element which collectively form a concept. Also here, the generated samples are not very sharp, but apparently it's enough for the model to replay, and it alleviates forgetting to a high degree. Okay, after this work, we thought how we can even push further for a more realistic setup of continual learning, in which a data stream comes batch by batch, and the model has to be trained in an online fashion on this data stream. So no sample can be stored in any form, no sample between the task to replay, and even no samples between the batches to be used. So purely online. We also found using additional network, for example, generative model, which we use also in the previous works, is another limiting factor which should be removed from the pipeline. The main reason for that is that the generative models are often large in size and can also potentially violate the privacy constraint. So we decided to remove all of them. And surprisingly, we found that almost all continual learning methods implicitly or explicitly neglect this constraint. So we proposed memory constraint online continual learning as a novel task at ECCD conference last year. To solve this task, we proposed a variant of distillation loss, which works on a batch level. Here, you can see a typical pipeline for a model in a memory constraint setup. After a batch is received, a training step is performed, and a memory is fully cleared before receiving the next batch, and then the next batch, and the next batch, and so on and so forth. So, well, we should make sure that at any time the model could potentially be queried and used for the inference or evaluation. Now let's look more closely at how this model is actually trained. Batch level distillation has a two-stage pipeline. At first, it's so-called warm-up stage, where the network is getting prepared for distillation. The current batch B is fed to the model. The output of the old classifiers are stored in a probability bank, Y hat, and in the same time, the task loss is computed, and current head is getting a small parameter update. And then in the second stage, we use the same batch of data B and the probability bank Y hat, and optimize jointly the new task loss with the distillation loss. Well, to balance these two losses, we use the norm of a gradient, in the warp stage, and simply reweight adaptively the gradient computed by these two losses. To explain intuitively what's going on here, I can say at time step T that we only have a batch of samples from the current task and no sample from the previous task. We update the head of the current task using the data that we have for it. But for the other task that we don't have their samples anymore, we at least make sure that the output logic for all other heads do not change after the latest gradient update. So basically, you can think of it as exploiting the data of the current task to somehow mimic the data of the previous task and enforce the output of the previous head to stay as unchanged as possible on this data. There's also an informal interpretation of that, which I will skip because of the time. Okay, now let's look at the results. So evaluated our method on different benchmarks and compare to a variant of our methods, L2 and distillation loss against some baseline. I would also try to skip here, again, because of time. And so, of course, the result that I show here is comparing against existing methods, and we outperformed them in benchmarks and different settings from different multiple tasks, and also here we show the comparison to the different method in terms of the memory overhead, yeah. Okay, so after this work, we thought how we can even push further and make our continual learning setup even more realistic. So we thought, given the open nature of continual learning, we cannot always expect that the semantic labels are available during the course of continual learning. So it's kind of unlikely that we can provide direct and constant supervision to our model or agent in every new environment or setting. So we moved our setting toward the open set recognition in an unsupervised setting, where no label about all new coming classes are available, and the model itself should discover new classes and classify the unlabeled samples into different semantic categories. So this moved us toward a new challenge or task, which is called novel class discovery, that this ICCP paper that is going to appear in a couple of months is on that problem. So this task is relatively new in the literature and should not be confused with unsupervised clustering, which is a static partitioning of sample to a bunch of groups or cluster. It's kind of more dynamic because we are first provided, the model with a set of labeled data to learn some basic property about the world, like a child in early age with parents. But later the model should not be faced with a large pool of will be faced with a large pool of unlabeled data, and it should automatically discover new concepts and learn to recognize them all. So let me define this task here a bit more formally. In a typical scenario for non-novel class discovery, you're given with two sets. The first set is the initial small set of labeled samples, with semantic labels is kind of similar to supervised learning. And there's also an unlabeled set of samples from the classes which does not have any overlap with the label set. So this is a setup and the task is, given these two sets, learn a single model which can discover novel classes. So clustering the unlabeled set into a set of meaningful semantic categories while keeping a high accuracy also on the label set. So what I need to mention here is that this problem is similar but different with semi-supervised learning, because in semi-supervised learning, the working assumption is that labeled and unlabeled sets share the same classes. But here we have new classes coming. Is more kind of continual learning where the new concepts or classes is getting presented to the model. So there are a bunch of methods proposed in the last couple of years for this problem. They introduced different supervised and unsupervised objectives for solving this task, which usually involve multiple specialized loss terms for the labeled and the unlabeled set separately. Lots of them use also different type of auxiliary loss, such as organizations, consistency term, and to somehow align these two loss terms a bit more, better. However, having these complex objectives makes optimization of this type of a methods very complicated, as it requires to tune lots of hyperparameters for each of these competing objectives. So in this work, we decided to unify this objective, simplify the learning by exploiting a generic loss function, which can be computed jointly on both sets. The general idea behind our method is to combine these two sets. We train an encoder with separated heads for each of these two sets, and then use a single classification loss, say cross entropy, for the labeled and unlabeled set in our training set. For the labeled set, the ground truth is given, so easy. You can just use them to compute the cross entropy loss. But for the unlabeled set, I've used Sinkhorn algorithm, as in this paper, to generate the pseudo ground truths. So for those of you who are not familiar with Sinkhorn, you can think of it as a learnable clustering network, which gets a bunch of unlabeled sample, partition them into some groups, and assign the group ID or a cluster prototype as a pseudo label to each of the unlabeled sample. So now we have real and pseudo labels for all samples, so we can just compute the cross entropy loss and learn the encoder with both heads and also the Sinkhorn network itself all together in an end-to-end fashion. So this is just like a very general idea behind our work. But now let's look more closely on how this model is actually trained. So we have two sets labeled DL and unlabeled DU that are shown in green and blue for clarity. For example, we have a bunch of samples of two class, horse and dog, and supervised, and some other samples from cat and giraffe. But of course, we don't have the samples of cat and giraffe because it's unlabeled. And the task is to learn a joint model which classify all of this for classes. So we start with selecting randomly some samples from these two sets and create a batch of images. Given this batch of samples, we generate two views of each image using random transformation. You can think of it as a random set of predefined augmentation. Here, for example, we see cropping for the dog and a bit of color jittering for the cat, but it can be any type of transformation which modify the image content, but keeps the semantic of that class and that image unchanged. Then we pass it through an encoder network with two heads, one for each set. So a head for labeled and a head for unlabeled. What I need to mention here is that the weight of the encoder and the heads are shared for two views, and we just showed it here like this for the sake of clarity in the rest of the pipeline. So this is only one model we have, and it's the model we're gonna use in the end for the inference time. So we feed the batch into the network, and our model predicts the probability distribution over all classes, I mean labeled and unlabeled classes for each view. So the sketchiness you see here shows the uncertainty in the logit that we see only for the unlabeled part, and we don't have this uncertainty because, of course, on the labeled part. And so for the labeled head, we have this logit prediction, and of course ground truth, which is the class label for the label set, and 0 for the unlabeled set. So we can directly use it to compute classification loss on the training set. But on the unlabeled set, we use the Sinkhorn clustering algorithm on the unlabeled samples and generate the pseudo labels for each view, and pass 0 as the pseudo label for the classes of the label set. So this results in two set of pseudo labels, I mean, for each view, which are independently clustered using the Sinkhorn algorithm. We can directly use these two pseudo labels to compute the loss, but to align and enforce consistency across these two views, we use the clustering assignment of each view as the pseudo label for the other view. This swap cluster assignment is very important step in our method, which is inspired by SWAP. This paper you see here on self-supervised learning from Facebook AI research. It encourages the model to learn an invariant representation with respect to the augmentation and distortion. Basically, involving representational learning into our pipeline. And finally, we stack the probability distribution or logic prediction for the two-head in conjunction with combination of ground truth and pseudo-ground truth labels, and use them jointly to compute the cross-entropy loss and backpropagate the error to update the weights of the network and continue this paradigm for the next batch and next batch until convergence. All right, now let's look at the results. We have evaluated on different benchmarks and compared against state-of-the-art. For NCD, we reported classification accuracy for labeled set and average clustering accuracy for the unlabeled set, which gives the accuracy of a clustering no matter what the actual label of any cluster is, as long as the member of a cluster are together or from the same class. So you see here on top, average cluster accuracy only on the unlabeled samples, which are on the training set, and the bottom, the reported accuracy on both labeled and unlabeled set from the test set. As you see, we outperform more classic methods like k-means till the more recent ones. Although being simpler, having only one loss does not require extensive hyperparameter tuning. But what's probably more interesting here to see is the behavior of our method in a more complex scenario like continual learning, and comparing it with the best existing method, which in this case, we picked ranking statistics from ICLR last year. You see here to compare somehow. So in the left, you see the average clustering accuracy with growing number of the unlabeled classes. So X here is the number of unlabeled classes, and Y is the accuracy. So we see here that the accuracy decreases for all methods as the task become increasingly difficult. It's mainly because of the growing complexity of the task with increasing number of the classes. But when you're normalizing it and compute the relative improvement with respect to, for example, ranking statistics in right, we see the margin is even growing by increasing the number of unlabeled classes, which is showing that our method is more adaptive to work in a more complex scenario like continual learning setup. But of course, still more exploration is necessary to be done to prove that, which we left as the future work. Okay, so good. So to summarize, continual learning is a way to go with the growing pattern of the data curation that we have now, given the fact that it's also somehow similar to how humans learn over time. This is for getting forward and backward knowledge transfer and model scalability, which needs to be tackled in a continual learning setup. And we show generative replay. It can be effective when we don't want to save raw samples for memory and privacy reasons. We also proposed a continual learning, online continual learning task, with extreme memory constraints. And for that, we showed that the distillation can be done in a batch level, simply like in a batch level. And finally, we explored continual learning beyond supervised learning and proposed a self-supervised learning method to tackle novel class discovery task. Okay, with that, I conclude. I think I'm a bit ahead of time. Thanks for the listening, and I would be happy to take questions at this point.
Thank you so much for your wonderful talk, Moin. Yeah, thanks for the very deep insights that you were presenting. You can see the questions too, right? That are in our comments. Would you take? There are essentially two questions. Would you take these?
I actually don't see the question. Yeah.
So it's yeah.
So, so I think this question is, continual learning makes me think of system identification with forgetting factor. Is it something related? I don't know what is system identification, so so I really cannot answer that. But if there's a factor, forgetting factor, which is because of I would say I mean, it's hard to tell, but I mean, it happens to the to continual learning because of the stochastic descent. Because I have this figure, the GIF, which was two guys was pulling the rope, and one of the slides, it's basically the nature why it happens. Two people, two, let's say, component are fighting together, and at each moment only one could be winner. So they pull toward themselves the parameters, and they're fine with that. But then in the next batch, the other guy pull the rope, and if something like that happens also in your case, it could be the reason. It could be similar. Okay, now, no models use backpropagation for learning tasks, but Bayesian approach, Kalman filter, was designed for continuous learning. Do you see such models being used in future for continuous learning? Well, I mean, Bayesian approach are, there are a lot of methods are using Bayesian statistics and Bayesian learning for continual learning. I'm not working on that, but I agree that because it's a setup that uncertainty is directly and organically is modeled inside that. I think this is going to be like one of the future solutions for that. I mean, I recommend you looking at the works in Trevor Darrell's group in UC Berkeley, which are using a lot of Bayesian learning for continual learning.
Cool. I guess these were the two questions that came from the audience. I have two questions too.
Sure.
So going back to novel class discovery. So say, what are these new classes? I mean, I can understand that new classes are discovered, but do they agree with what you as a human being would identify as a new class? So is the mathematics, so to speak, in line with what we humans would like to see? Could you give, you give this very simple example of dogs and cats. Say what would be a new category that would emerge by only having this as labeled data?
Okay, that's a very good question, actually. So, I mean, the current setup of novel class discovery, they follow the definition, the semantic labels that is provided in existing data set, the same level of granularity that you have in the label set. For example, if you have cats and dogs in your label set, you might have, giraffe, I don't know, zebra in your label set. But I agree with you that if you really consider different level of granularity, you can imagine having, one class animal or like even like more fine grained that type of zebras probably exist. So I think this is so in the way that we currently solve the problem, we assume that the level of granularity is kind of same for labeled and unlabeled, and then try to find the clusters, meaning that the finding partition or label set to sort of predefine categories which are semantically more consistent or coherent, right? And but I mean, in the current setup that we also evaluated, and every element evaluates, is they assume that the number of unlabeled classes is given, right? Which is another, let's limiting factor if you want. So if you're providing the number of k for k-mean, say, you're defining somehow the level of granularity, and also the data sets you're testing, and also the people are testing, it's kind of ImageNet like. So it's like in a level of fine grainity which is easy, let's say, but I see where you come from. I mean, what if we have different definition than or model while learning? But I mean, I think the nature, this label set is designed to be attached for somehow solving this definition problem, because we provide the or baby with some definition about the life, and we cannot expect the baby can be very different in adulthood after that. So it's especially now the current setup. Usually, the number of classes in the label set is more than the number of classes in the unlabeled set, which is yet another limiting factor.
Okay, thank you. In your introduction, in the very beginning, you mentioned very briefly GPT-3. My question is the method, the idea, your proposal that you have presented tonight. Would it be also be applicable to natural language processing? And I'm specifically thinking about these big pre-trained transformer-like models. All the things that you mentioned that makes it impossible to so to speak replay the data is impossible because you don't have the data, right? And I guess that too, it's like, of course, for most applications you need to fine tune, but as you said, probably at the beginning you start losing things, right? So is it possible to apply it to this type of problems?
I'm not aware of any work doing that currently, but I see that this is going to be like one problem that also continual learning community should look at. There are two problems here. One is the problem that you're targeting in the current literature is growing the number of semantic category that we see in the continual setup. Right, so we see cats and dogs, and then we add giraffe and zebra, right? And then there's another problem, which is continual adaptation, which is basically more on the feature space. The samples are changing, over time. Maybe one concept is in one way, and maybe next year is going to change, or like imagine like Twitter type of things, which is like a trend should be captured. So I think these two problems, continual learning, which is more on the semantic. Labeling the concepts, like more supervised way of looking, and also like continual adaptation are somehow getting closer. So, and I think at some point, if we can really tackle this problem jointly, I think we can expect to see methods coming for things like language models or language generation, which kind of unify this two view to have a models which are learning adaptively. But I mean, on papers, the existing solutions for continual learning can be used also for transformers or language models. But I think the point is that if it's going to be providing any benefit or not, especially because the say GPT-3 is learned on all possible data that we could possibly have. So having something better is very hard to imagine.
Yeah, no, I mentioned that like for typical applications, you need to fine tune to get the things that it's too general, so to speak, and then probably you also forget things. But yes, I understand your question. Thank you very much. There's one last question that showed up. Could you take that one question too?
Yeah, please? Sure. Just a note, when you showed the slide with backward forward learning, I was wondering if there is a mechanism process of eliminating as well, which is a novel class discovery, as I get it. I mean, backward knowledge transfer is a very general term. I mean, you can think of it like modifying the knowledge, right? In a backward sense, the modifying can come with growing the knowledge. It can come from eliminating the knowledge or modifying the knowledge. So there are not a lot of methods actually doing backward knowledge transfer these days in continual learning, and it's a very, very difficult one. But I think eliminating or like removing part of the knowledge which is not valid anymore, which is not useful anymore, can also by definition can be a backward knowledge transfer. And the relation to novel class discovery for that is. In novel class discovery, we don't have that much of impact of the unlabeled sets on the labeled part. So it's more like driver is mainly the labeled set, and the unlabeled set is somehow coming after. So in that sense, I mean, I see also less similarity.
Cool, Moin. Thank you again very much for your wonderful talk. I hope we meet in 1 year from now at live at SAP headquarters here in Berlin. That would be nice.
Hopefully, yeah.
Yeah. Again, also thanks to SAP for having us, albeit virtually tonight. And to the audience, I would say we will be happy to stage your talk too. So if you have something small, something big, you want to discuss a paper that you just read and where you're excited about, just give us a shout, and we're happy to stage you. Thanks also to Abhishek for using this new software, which looked really, really nice. And yeah, we'll be back in a month from now. Again, thank you, Moin, for everything.
Thank you for hosting.